Hello everyone, I'm Weiliang from Huazhong University of Science and Technology. I'm glad to share our work. This is a joint work with QCII, IIS, and School Foundation. Unfortunately, my co-first other Qian and myself couldn't get our visa in China to be here, so I present our paper remotely. Now let's begin. What is zero knowledge proof? Zero knowledge proof is a cryptographic protocol which contains two parties, the prover and the verifier. They know some public information, such as public function f, input x, and output y. Prover claims that he knows a secret input w, such that the output of function with x and w is y. The secret w is private information, only known by prover. Zero-knowledge proof requires prover to generate proof pi, which is zero-knowledge and reveals nothing about the secret W. Then, prover sends proof to verifier. Verifier could check the validity of proof to determine whether prover knows the secret W. There is a special kind of ZKP protocol, ZK-SNARK, which is the abbreviation of Zero-knowledge switches no interactive argument of knowledge. ZK-SNARK can generate a switches proof for any program and support faster verification of the proof. Due to these properties, ZKP has been deployed in real-world systems of blockchains and cryptocurrencies, and it has potential to be used in many privacy-preserving applications, such as verifiable machine learning, electronic voting, and online auction. However, the efficiency of proof generation by prover is very low. Usually, prover runs on a machine with strong computing power, such as cloud servers. For example, it takes days to generate proof for verifiable machine learning inference, while the verifier could check validity of proof within milliseconds on mobile phone. The acceptable latency in real world is within seconds. Such a long latency makes it impractical to use in scenarios like real-time payment and decentralized trading transactions, despite its great benefits in privacy protection. So we want a faster prover to make ZKP truly useful. A typical proof generation process in prover mainly contains two stages, polynomial computation stage and multi-scalar multiplication stage. More specifically, for first stage, prover multiplies polynomials by using a number-theoretic transform algorithm, and all arithmetic operations are based on large finite field. For next stage, prover performs multiple multi-scalar multiplications based on elliptic curve, and each MSM entails many point multiplication and point addition operations, which are very time-consuming. These two stages account for more than 90% of the proof generation time. So our work is focused on improving performance in these two stages. We propose GZKP, a fast GPU-accelerated zero-knowledge proof system. It contains an entity model which promotes a cache-friendly memory access pattern. It allows threads to perform on-the-fly and internal shuffling when transferring data. An MSM model which effectively consolidates redundant computation and explores fine-grained task parallelism with load balancing. And GZKP offers at least an order of magnitude performance improvement. Let's start with first stage. NTT is variant of fast Fourier transform that applies to large finite fields. It has multiple rounds of iteration calculations, and each iteration contains lots of butterfly operations. Each butterfly operation performs large integer multiplication and addition. The bitwise of the operand is at least 256 bits, and the distance between two operands of a butterfly operation increases exponentially. For example, the operand of first butterfly operation are A0 and A4 in iteration 0, A0 and A2 for iteration 1, and A0 and A1 in iteration 2. Such irregular memory access pattern brings significant overhead. The NTT computation can be parallelized by dividing iterations into batches, such that each group of independent butterfly operations works on a subvector. Each of such independent groups is naturally mapped to a GPU block for parallel computation. Previous solutions perform costly reordering of input array at the beginning of each batch, so that the next iteration can use purely contiguous access. This step is called shuffle stage. However, with large bitwise used in ZKP, many batches require more such shuffle stages, each costing 42 to 81% of per batch execution time. When we load data directly from global memory to shared memory instead of using data shuffling, hit rates of layer 2 cache is very low. We find that its cache data are also depended on by other adjacent independent groups. However, due to that large adjacent groups are mapped in different GPU blocks, this cache data cannot be used. To improve cache efficiency, we design a cache-friendly GPU-based entity model. The key idea is that our entity model performs on-the-fly and internal data shuffling when transferring data to ensure contiguous memory access. First, rather than having each GPU block work on one large group, we assign it to multiple smaller ones. This allows GZKP threads to perform internal shuffling when transferring data between the global and the shared memories. In each round, threads access contiguous elements from the global memory that can be well coalesced. They then write data to appropriate location in the shared memory, producing desired threaded interleaving pattern. At last, these threads are mapped to different independent groups to calculate butterfly operations. For second stage, MSM performs in the product of scalar vector and point vector. Existing work use Pipenge algorithm to reduce complexity. First, it uses sliding window to split large bitwise scalar into multiple parts. Then all points are within each window are grouped by scalar components into buckets. With the distribution law, it replaces expensive point multiplication operations with small point addition operations. Then, points are summed up in buckets, multiplied with corresponding bucket scalars and summed, and finally accumulated across windows to get the last result. The scale of input vector is up to billion. Previous work explores data parallelism by decomposing the computation horizontally into multiple sub-MSM tasks. Each sub-MSM can be naturally assigned to a GPU block, where algorithms like Pipenge are further adopted. However, there are opportunities of alleviating redundant computation between different sub-MSMs. For example, the step 2 and step 3 in different sub-MSMs could be merged to save point multiplication operations, and the existing solutions suffer from significant load imbalance overhead caused by sparse state distribution and large bitwise integer. To address these challenges, key idea of GZKP is that we effectively consolidate computation and alleviate redundant expensive elliptic curve operation, and we also utilize fine-grained task mapping to ensure load balance. First, we hence discard sub-MSM partitioning and instead consolidate all computations in each window. Then, we pre-process point data, merging different windows to one window, and there are only a bunch of buckets left. We analyze the load of each bucket and sort them by load. Then, we schedule buckets in order, starting from the buckets with the heaviest load, ensuring that heavy buckets are not left as stragglers. Our experiments are conducted on a server with dual Intel Gold processors. It's equipped with 4 NVIDIA Tesla V100 GPUs and 1 NVIDIA GTX 1080 Ti GPU. And we compare GZKP with multiple state-of-the-art ZKP systems based on the ZK-SNARK protocol. First, we evaluate end-to-end proof generation time, some of the polynomial computation and multi-scalar multiplication stages, using ZK-SNARK workload and Zcash workload on one Tesla V100 GPU card. GZKP accelerates state-of-the-art CPU-based and GPU-based solutions by up to 78 and 48 times respectively. For NTT model, we examine execution time of a single NTT operation on different platforms. GZKP outperforms state-of-the-art CPU-based and GPU-based solutions by up to 700 and up to 20 times respectively. For MSM performance, GZKP outperforms state-of-the-art GPU-based solutions by up to 18 times on V100 GPU and by up to 9 times on GTX 1080 Ti GPU. In summary, what GZKP brings to ZKP system? GZKP provides targeted optimization for ZKP proof generation and brings significant speed up towards making ZKP truly usable. That's all, thanks.